guess you're all familiar with the Doppler effect. It this always surprises me every time I hear an ambulance. You know, you see the fish going up and down. So how do we cast this effect in mathematical terms? This is the first point of this lecture. The second point is how do we deal with the Doppler effect in the context of radar remote sensing. Now, again, we go back to the formula for the received signal. You know that you transmit a certain signal, and what you receive is g of t minus the distance times the phase. Okay, so this is the received signal. This is without the amplitude factor, because I am not interested today in discussing the intensity of the signal, so I just drop this term. And this is after the modulation, but before matched filtering. So G is the transmitted pulse. Let's say the transmission is G of t times the carrier. Okay, so where r is the distance from the radar antenna to the target. So what happens when the target is moving? Of course, if the target is moving, then there is no a fixed distance. So this object is going around, and so it's r of t. And here we are. Okay, so how do we deal with that? The first clever thing to do is to approximate. Is that okay? Is that fine? Okay. So the first thing to do is to approximate the distance. So I do this like r of t is equal to r of let's say 0. Let's say the distance at time 0. By time 0, I mean, for example, the transmission time. So I am imagining here that I transmit my signal at 0, and then I get it back here. Or whatever reference time you like. Plus the derivative of the distance times t. And the derivative of the distance is the radial velocity. So this means that you can approximate this signal this way. So first thing first. So this term is a problem for you, meaning that this term, this velocity, is telling you something new only if it is radial. So if the target is moving along the sphere, so if the target is moving but it is not changing its distance from the sphere, then this term is zero and there is no Doppler effect at all. Okay, this is important because there's so many errors on this point. Then what you have, so assuming that there is a variation of distance with time, so assuming that there is a radial velocity, you have two effects. The first one is that your pulse is dilated or contracted depending on this radial velocity. You can write this as you can write this pulse as g of t times 1 minus 2 Vr divided by c minus the delay. And this is a contraction factor. So this means that your signal is a bit contracted, so it is either shorter or larger, depending on Vr. So if this is your g of t, then the signal can go a bit larger or a bit shorter. Is this really the case? Well, you might want to notice that this dilation or contraction factor is 1 minus the ratio between the target velocity and the speed of light. Okay, so unless you are getting the signal backscatter from a starship, I would say that this term can fairly be neglected. Okay, and this is what we will do in the reminder. So we will neglect this dilation or contraction of the pulse. Okay, what stays is this term, this phase. And why? Well, we can see why. This is given by, so this is a term that you can rewrite so let's say then that we further approximate this as g of t minus the delay. So I'm neglecting the velocity here. Then okay, then I have the phase. So the constant, the constant part of the phase, and this other term, which I write this way: 2 pi times the Doppler frequency times t, where the Doppler frequency is twice the radial velocity divided by lambda. You can immediately see that this is not negligible, because if you assume, for example, if you are working at a frequency of, let's say, X band, so which is a quite typical case, and by the way, it is the case of the exercise we saw last week, then lambda is 3 centimeters, and you can see that if you have a speed on the order of, I mean, how fast does a car go? Let's say an average speed can be 50 to 100. Oh well, 100 is a lot. Let's say 30 to 60 meters per second. And then this term can be several hundred of hertz. So you are sensitive to this Doppler frequency. Okay. So this is the reason why we shall approximate the signal this way. Now, what are the effects of this term? We say that, so this is something that we know now, so I just take it here. So we say that the received signal is processed by assuming matched filtering. So we know that our received signal will enter into a low-pass filter, which in the time domain it is the opposite of the time reverse of your replica. In the frequency domain, this is the complex conjugate of the Fourier transform of G. So, let's do this in the frequency domain. So, if this is your signal with the Doppler, SR of T, so the Fourier transform of your signal is this is G of F, and this is multiplied by a complex exponential, and so you have a translation in the frequency domain. And so you have up to some terms, let's say up to some phase term, which I'm not interested on focusing your attention on. You have G of F minus Fd. So basically, what you are receiving in the frequency domain is not your original signal, but it is translated in the frequency domain by an amount Fd. Of course, when you are doing your matched filtering, then you are again letting this signal be filtered by the same G of F. And so you see that in the frequency domain, your filter is no longer aligned to your signal. In the extreme case where this Fd is larger than the bandwidth of your signal, then you get 0. Because in this case, the signal slips completely away, completely out of your filter. And so you just get 0. So you do your radar experiment and nothing gets out of your filter because you have a Doppler frequency. So how do you deal with that? Well, I like to start from a very simple scheme, and since we have seen that the problem here is that the frequency is no longer matched, so the idea could be to try to compensate for this frequency, and then do your matched filter. So the scheme of your receiver in the presence of the Doppler frequency would be something of this kind. You counter-rotate the signal by the Doppler frequency, and then you apply your matched filter. So you are just cancelling this term out this way. So everything is perfectly recorded. Yes.
Non ho capito qual è il problema se non corrispondono le cifre questi.
In English.
I don't understand the problem if they don't match the frequency.
Well, imagine, so let's say this is your filter. So this is the frequency representation of your filter. So it just accepts frequency component here and kills everything else. So if your signal has a Doppler frequency, then it moves in the frequency domain. If it moves here, then it is completely filtered out. Okay. So, and this says, let's say, this context, a clever thing to do is to just counter, rotate your phase so as to cancel out this complex exponential. Of course, this works. To do, yes?
But we must know.
Yes.
in advance.
Yes, exactly. Yes, exactly. To do that, you need to know the Doppler frequency. So maybe in some cases I do know it, so you can predict it because I don't know, maybe your system is very stable and so you can assume that you know the velocity. But if this is not the case, which is the
Some feedback system.
say it again.
If we use some feedback system to track our FD,
Well, I might be proposing something of this kind now. So, if this is not the case, then what you do is that you try with different value of this Doppler frequency. So, just to clarify the notation, let me call this is R0. This is the distance of your target from the radar at time 0, and let's also call this FD0. So where 0 in this case refers to the true distance and Doppler frequency of your target. Okay, so what I want to do is that I want to apply this scheme here, and for a number of different Doppler frequencies. And so instead of getting a single signal, which is a function of time, I will get a signal for each value of Fd. Okay? So what I want to produce here is a new signal, call it capital S, which will be a function of time and Doppler frequency. So be careful, this is a two-dimensional signal because it is a function of two real variables. Okay. In practice, if you want to express this mathematically, because I like block schemes, but I need an equation to really understand what is going on, then you will get something like this. So the expression of this signal, I wrote T, let me write tau now, because I like this better. So S of tau and Doppler frequency, this will be equal to your received signal so that one, which we try to compensate by the Doppler frequency real time in the T. Yeah? This is what you do. And you end up with a function. Now let me try to represent it. So something like this is tau and this is the Doppler frequency. So I will end up with a function with some shape. I hope this is clear. So the position of the peak of this function will tell us which is the true delay, so which is the true distance of the target, and which is the true Doppler frequency, hence the true radial velocity of this target. Huh? This is what I want to do.
Sorry, the mean value are the real Doppler frequency and the real time. The center of this Gaussian
The peak.
shape will be
The peak is
the value of the peak. The value of fd on the axis fd and on the axis
tau.
tau. Yes, the value that describing the center point.
No. I am trying all the tau, and so I want to build this function for every value of tau and of fd, so for every pair tau and
okay.
fd. This is the peak. This is fd0 and
Okay, exactly.
r0.
And these are two.
Okay. This is the reason why I wrote 0 here.
Exactly.
To disambiguate the two. Okay, so far so good. This is how you handle a target with a velocity. This is how you model the signal. We did a lot. So we started by talking about an ambulance. Now with that characteristic pitch variation. Then we modeled this in mathematical terms, and this is the mathematical model of the signal. And here we have a scheme. Here we have a mathematical description of the procedure which will give us the way to estimate the distance and the velocity. Okay, so the distance through time delay, and the velocity through the Doppler frequency. Yes?
I don't get why do we have the matched filter in that interval? Because that was the signal out from the matched filter. But
Because you're right. I'm sorry and thank you. Yes, absolutely. Absolutely. Thank you. It is written here. Of course. So you have the signal. So the signal is, we say, counter-modulated, and here the matched filter. Thank you again.
That's the convolution between the input and the matched filter.
It's the convolution between the counter-rotated signal and the matched filter. Yes. This is exactly in the block scheme. Blame on me. Okay. And okay, so now we know a lot. We do not know the whole story yet, because I think that so the first question is how many frequencies do we need? And what is our accuracy about the estimation of the Doppler frequency, and how does this translate to the estimation of the velocity? So this is just a method, but we still know nothing about the performance of this method. And also, we still know nothing about how to implement this method. So, how to do this? Let's start from a simple case. So let's start from a simple case. Now, what I want to do is I want to introduce the property of this function, and to do that, I will plug the expression of the signal in here. Okay, so in this case, I would assume that I know the received signal, and I do that because I want to study the property of this estimation technique. So we have okay, so I plug the expression of the signal in here. Before you ask me, I dropped this term here because this is just a constant phase and I am not interested in discussing this phase here. But of course, if you want the complete expression, then you should also remember about this term, okay? But I will not include it here because I'm not interested in this term. Then I will do one more simplification, and this will be that I will assume that R0 is 0 and Fd0 is 0. Why I do that? Because you see that whatever analysis I will do here, this will always be a function of tau minus 2R0 divided by C and Fd minus Fd0. So I can do a very simple shift of the axis and assume that these two are 0. Okay? Is everybody fine with that? So don't write me desperate, say, yeah, professor, why is it 0? Okay, yeah, this is just a simplification. So we end up with this very simple form. Now, this is a function of two variables. So let's start by studying its sections. Is that a mistake?
E at minus J2 pi.
Minus, okay. So, let's study the sections of this function. Let's study the section for Fd equal to 0. What do you get here? This is gt times t minus tau in the t, and this is the autocorrelation function of g. Oops, as a function of tau. So nothing else that the matched filter. We already saw, no? And this is the energy of g. So, and this tells us that your resolution, your time resolution, depends on how wide this peak is, and this is more or less the inverse of your bandwidth. So your resolution about tau is 1 slash the bandwidth, hence your range resolution is the speed of light, half the speed of light divided by the bandwidth. We saw this already. So now let's do the same for the other section. The other section is S of tau equal to 0 and Fg. So what you get here is the absolute value of G. And so you get that this section is the Fourier transform of the absolute value of your pulse. Let's make it simple, and let us assume that the absolute value of G is just a constant with some duration t. So this t is the length of your pulse, and then what you get is that this is the Fourier transform of the constant, and so this is proportional. Let's write it here. This is proportional to a cardinal sign. This is equal to a cardinal sign. And so this is the section for Fd equal to 0. The section for tau equal to 0 is given by this expression. And its graphical representation is something like this. This is a function of Fd. So this is the peak. The peak is in 0, of course. And the first 0 is in 1 divided by the observation time. And since you all gave an exam of signal, you know that we say that the effective width of the lobe is 1 divided by the time. So this lobe gets narrow and narrow as the length of your pulse increases. Easy, no? I guess you all remember what we said about range resolution, so the capability to resolve two targets, meaning that if there are two targets, I say that two targets are resolved if they appear as two peaks. We say that for range, if we do the same in frequency, then two targets are resolved if they adopt their frequencies is larger than 1 over t. And so the frequency resolution of your system is 1 divided by t, so the length of your pulse. And of course, we say that the Doppler frequency is equal to twice the inverse of the wavelength times the radial velocity, and so this means that your resolution in velocity is given by the wavelength divided by 2t. No, sorry. Is yes, meter per second. So it's correct. That is to say, if you just multiply this by half the wavelength, then you can cast this graph directly in the as a function of the radial velocity, and this is your resolution, so the width of your loop. Okay. So now a question that you should be able to answer very well. Let's imagine that you are building a radar to estimate the velocity of some target. Then let's say that you want to detect the velocity of a car. So a car cannot go fast. So a car on open street cannot go faster than 300 kilometers per hour. Is that accepted? Okay. So this means that you want to prove all the possible velocity from plus to minus 300 kilometers per hour. So this is your maximum velocity, this is your minimum velocity. You know that you are capable of resolving targets as long as their velocity is, as long as the difference of their velocity is larger than this value. So how many Doppler frequencies do you need to test?
The max minus divided.
With some margin, if you like, you can assume a factor 2, but this is there. So you can divide this in the number of intervals whose size is no more than this delta VR. Okay? And this is it. So you know exactly how to sample this function. If you like, we say that you can allow some margin. And why? Because if you sample this way, then it means that you are taking this value and then this other value. So, but of course the Doppler velocity can be, so every velocity is valid. So you could end up in sampling these two values. And so if you want to ensure not to lose too much intensity, then you can simply use finer sampling like this. So at most you pass from like here to here. You're not convinced? The lady here. You're not convinced? Okay.
I'm not convinced.
Oh, bravo. Okay. Because I didn't explain it the right way, because it's really easy. So my point is that imagine that you are running this experiment, and you are using a certain set of Doppler frequencies. This means that you are testing, for example, this value, let's say this particular value and these other values. Your cardinal sign is what you get with a continuous set of Doppler frequencies. So it could as well be like this with the peak here. Let's see. It could as well be done like this. And so in this case, you are not sampling the signal in the peak, but you are just sampling here. And so you are losing intensity. This is the point. And why is it never good to lose intensity? Well, in the first place, because if you just see these 2 points, then what is the peak? You just don't know. The other point is that you always have noise. And noise is the same everywhere. So if you are not taking the peak, but you are sampling this function away from the peak, then you are degrading your signal to noise ratio. Okay? Did I answer better now?
Yeah, but the point is that by saying sampling, that means that we are trying different Doppler frequencies.
Yes, of course.
That's the point.
Absolutely. You have to decide a priori which Doppler frequencies you are testing. Absolutely.
So it is better to have more
I would suggest to have more, yes.
with
Yes,
a
of
certain
course.
limit.
Yes, of course. But I mean, this is not done in hardware. This is done in software. So you have to sample your function. Now, an example drawn from the last time we met. We described this case of this surveillance radar. So you remember, you had this radar which was rotating, and it would emit pulse to detect aircraft. Okay, yeah, with some performance. We figure out that the length of the pulse, so your T, was 266 microseconds, yes. So what was not in the picture last time was the velocity of this aircraft. And so now the last point of this exercise tells you, assuming that the top speed of the aircraft is 1500 kilometers per hour. Oh, the wavelength was 3 centimeters. So this is the other data that you need. And you have to tell how many Doppler frequencies you need, assuming that you do not want to degrade the signal to noise ratio by more than 1 dB. And so let's say how many FD for SNR with Doppler be no worse than SNR Doppler, not dB, Doppler, B, no worse than SNR without Doppler minus 1 dB. Was there a question? No. So how do you answer this question? Well, the signal to noise ratio, you remember, is the peak of your signal after matched filter divided by the noise power. So this is the peak divided by the noise power. So now the noise power is always the same, but the peak will change as a function of which Doppler frequencies we are considering. And so basically this requirement is telling that if this is the cardinal sign which gives us the sensitivity of your system to Doppler, then we want to be sure that we will sample this function such that at worst we lose 1 dB from the peak. So this is what this exercise is asking us. So now 1 dB means that this is something that I checked with MATLAB. So 1 dB is yes. So this is the cardinal sign. The cardinal sign of 0.25 is equal more or less to 0.9, and this is more or less minus 1 dB. So this means that if you want to lose no more than 1 dB, then you have to ensure that you are sampling this function in a point that is no farther than well, such that so in this, I'm sorry, so in our case we had the sine of pi fd times t divided by pi fd. This is equal to the cardinal sign fd times t, and so we are requiring fd times t be equal to 0.25. So you are requiring that your frequency does not deviate from the true frequency by more than 0.25 divided by the length of your pulse. And sorry, I made too many passages at once, but I hope that now it's clear. And when you put the number in, then you get that your delta f, so this spacing in frequency, has to be equal to 950 Hertz. then we say that the maximum, so this was the maximum speed. So the speed in meters is, these were, I wrote it here. So the maximum speed in meters is about 470 meters per second. And so your maximum Doppler frequencies is about is about 25 kilohertz. You want, so the total interval is plus to minus FD max, so the number of Doppler frequencies is twice the maximum frequency divided by the delta. And this will give you more or less 50, so you get 52.6. So you need 53 different frequencies.
What is the difference between the FD max that we have found and the condition on FD that we have found previously?
FD max is the maximum Doppler frequency that we expect, because we say they cannot fly faster than that. We know that we will get a cardinal sign once we do. So if you assume to compute this for an infinite number of frequencies, so the best you can do, then you know that you will get a cardinal sign. If you sample this cardinal sign in the peak, then you get the same signal-to-noise ratio that you would get in the absence of Doppler frequency, because when you sample this in the peak, it means that you have perfectly compensated for the velocity of this target. You don't want to use an infinite number of frequencies, because you want to do other things in your life, and so you just divide this, and you don't want to lose more than 1 dB. So not to lose more than 1 dB means that you have to ensure that the frequencies that you are using are not can differ from the real Doppler frequency by no more than 0.25 divided by t. So this is your sampling, and this is your total range. This is simple, but for some reason it's never simple to explain. Okay. Hope it is clear now. Okay, now we can say much more about this, huh? Because now we did build this function to estimate both the position and the speed of the target at the same time, and we did not make any assumption about the shape of about the waveform we are transmitting. But there is much to say, and indeed this is really a very famous page of the radar theory, And for this reason, this function, so which is the expression of the signal after matched filtering with this frequency compensation, has been studied a lot in the literature, and it is called the ambiguity function. So let's say S as a function of tau and fd. It's called the ambiguity function. And why do you have this name? Well, because it is not always guaranteed that you can estimate a target's position and velocity without ambiguity. So what we did, what we saw so far is just an analysis of the section of this shape. So we saw that in the section where fd is 0, which means if you know the true Doppler frequency of the target, then you get this peak, so you can detect a targeting range. In the section where tau is 0, and so if you know the true distance of the target from the radar, then you can detect it, then you can estimate its speed. But we only saw a section. This can as well be something like this. For example, you get this section also from a function like this one. Let's say that this is time, this is the Doppler frequency. I'm trying to see this function from above. So I will draw this function with tones of gray here. If you have a function like this, so imagine that this is the peak, and then it goes down like so, this is your peak, and then it goes down. Then this is your section at 0 Doppler frequency, so you can use this to estimate the position. This is your section at 0 delay, and so you estimate its speed. But if you look at this function, then you just don't know if this is the real, this is the real position and velocity of this target, or this other solution is the true one. So you are ambiguous. If you want to build a function, so if you want to see how this happened, just assume that your g of t is a tree. Okay, so I am assuming a particular waveform now. So what happens? Well, you have, this is G, oops, with J. This is a minus J. So this square form you can express is t squared minus 2t tau plus tau squared. So the t squared is killed with this other one. This tau squared is just a constant phase, so it does not contribute to the result of this integral. And so you end up by integrating these expressions. So fd minus alpha times tau times 2. Okay. And this, you see, is a function of the difference between fd and alpha times tau. Alpha is the chirp rate. Huh? And so in this case, you get the cardinal sign of fd minus alpha tau and so in this plane, it just means that the peak is everywhere here. And so you are ambiguous, so you just don't know. Every solution is possible. Yes?
I don't get why in the third multiplicative term in the integral we have a minus at the exponent instead of plus.
Because there was a complex conjugate.
No, the last one. I mean. Not the one.
Okay. Sorry. So it's, but that one would be positive, so positive, negative. Okay. It doesn't change much.
No,
Even if this sign were wrong, then you would have it this other way. But you're right, of course. Okay, and indeed, there is a lot to say about this waveform. So the real question is, which kind of waveform should I transmit to avoid this very bad situation? This is the worst case. So imagine that you are building a Doppler radar to detect when bikers go too fast. And this is your ambiguity function, then people will always comply. Because you cannot just say if you had a biker at this range going very, very fast, or at this other range going very, very slow. So in this case, all the intelligence in building this kind of system is in the waveform. So this one, waveform. Now, let's go back to the general expression of the ambiguity function. Let's say let us just see two properties. Well, before we start, what is the ideal shape of the ambiguity function? We say that this one is bad. Huh? The ideal case is just a point.
Wouldn't the ideal function be one line, so to each tau corresponds just one FD and vice versa?
Because in the case we just seen, then you have the integral of the complex exponential of fd minus alpha times tau. So whatever the result is, you get a function of fd minus alpha times tau. So if the peak happens when this is 0, what are the pairs tau and fd for which this is 0? Everyone here, okay, every pair here is compliant with this condition. Okay. The ideal case, of course, is something like this. So you have just a very narrow peak, and you know your position speed very, very accurately. Of course, if the peak gets larger, then you are losing sensitivity, but you're still not ambiguous. So this is not bad. So what you would like to do, basically, is to shrink this volume. So this is a 2D function, right? So you have to imagine, let's see, very difficult to do, something of this kind, right? So what you want to do is to shape this thing so as to squeeze it into a single peak. And now my question is there a waveform that allows us to do that? Who said no? Now, two very important properties of this. The peak. The peak is always, you can have multiple peaks, or you can have a situation like this one, but it is easy to show that the peak is always is at most equal to the value in 0. So let's say that you always get a peak in correspondence of the true position and velocity of the target. The other property is that if you compute the volume of this function, so we say that we would like to reduce this volume as much as possible, because we want a single peak. So let's try to calculate this volume and see how it depends on the shape of the waveform. Then, unfortunately, you will just get that this is equal to the energy squared. So I have a beautiful demonstration with all the passages here, so I'm not lying, for these two properties, but I prefer to just show you a code which will help you understand much more. But in case you have mathematical question, here we have a demonstration. So this means that once we fix the energy of the signal, the energy is what we pay for. So once we decide the amount of money we have, there is nothing to do. We cannot reduce this volume, what we can do is to, let's say, distribute this volume so as to fit our scopes. So having a chirp is not a nice solution in this case. Let's see what the other solutions are. And for this I have my PC, my connector, so this is already in your folder. The name is Breda Doppler. Breda Doppler. In Italian, so again I do commit to translate all the comments for you. So this is so this code implements exactly what we have just seen. So here is just some parameters. This is the length of the pulse. This is the bandwidth of the pulse. This is the central frequency, and this is the speed of light. So those are the true position and speed of the target. So I am assuming a target at 4,500 meters away from the radar, and which is traveling at this speed. This is just the way I am setting the time axis. So this is the sampling interval of the simulation in time. Of course, I am assuming to treat a signal whose bandwidth is B. So to ensure some margin, I take a fourth of this value. And this is the time axis. I take it symmetrical with respect to the zero. And this is all you need to know about this simulation, because the rest is just that I am generating a pulse through this function which you have. So this is pulse, this is the time axis, the total length of the pulse, the bandwidth, and the waveform is, you can generate different waveform. This is the received signal, which I obtained simply by translating the waveform according to some delay tau, and you can do by interpolation. Then of course I am including the phase, so this S of Rx is exactly the received signal before method filtering. This is just a frequency analysis, so it is not interesting now, but here we have all the Doppler frequencies that I cover. So this is the axis of the Doppler frequency, and so you see that for each Doppler frequency I do a matched filter. First I try to compensate the signal. So first I try to counter-rotate the phase of the signal by the Doppler frequency that I am testing, and then I just do a cross correlation with the matched filter. This is it. So let's see what you get. Waveform 1. So waveform 1 is a cardinal sine. So I am transmitting a cardinal sine. So this function is very well localized in time, not so in frequency. So you have a large bandwidth and it is a very short pulse in time. And this is its ambiguity function. So this is already converted in range and velocity. Of course, it is the same if you do this in delay and Doppler frequency. And you see that the peak is uniform here. So by transmitting a cardinal sine, you are very sensitive to the target position, but you are not sensitive to its Doppler frequency. So if you just want to estimate the target position and you just don't care about its speed, just use a very short pulse. It is going to work beautifully. And this is just a close-up. This is just a close-up. Now let's pass to waveform number 2. In this case, it's more or less the opposite. So I am transmitting a constant waveform. So not a chirp, just a constant. So it is a very long signal in time, and it is very narrow in the frequency domain. And you have exactly the opposite situation, because in this case, this is your ambiguity function. You have some sensitivity in range as well, because the signal is long, but it is not infinite, and so you get some sensitivity. But let's say that emitting a single tone is what you have to do if you just want to study the speed of the target and not its position. If you transmit a chirp, there you go. So this is the chirp. And so now we have a signal that is large in times and large in the frequency domain as well. This is an up chirp, meaning that the frequency is going up. So it's from the minimum to maximum. And this is its ambiguity function. I don't know if it is very clear here, but it is not straight, so it is a bit tilted. And this is a close-up. And you see again, are we detecting a target at this distance with zero velocity and this velocity, or a target which is much closer and it's going like hell? So the signal is no good at all in this case. You can do the same with I don't remember which waveform is that. This is the down chirp, so we are just changing the sign of the exponent of the complex exponential of the chirp, and you get the same situation but with the opposite slope. Now, since with an up chirp we get this shape, with the down chirp this other shape, what I can do is to try to transmit them both at the same time. So in this case I am transmitting the sum of a chirp with the sign minus and the sum of the chirp with the sign plus. What I get is now a single peak. You see? So this is much better, I would say. Of course, this is a zoom on the maximum. You have a single peak. You also have this other thing which could disturb you. So in the case that you have a lot of noise, for example, one of these points could become taller than the peak. But you have many solutions. Another solution, let's say waveform 6, I don't even remember what it is. So waveform 6, here we are, right, in this case we have a triangular chirp, so that the frequency goes up and then down, and more or less I get the same. Waveform 7, this one looks good. So in this case we have a single peak, so this one really looks good. And let's see. So truth is that in this case we have a lot of peaks. So this is our ambiguity function, and the waveform that is giving us this particular ambiguity function is a train of cardinal signs. So I am transmitting many cardinal signs, and what I get is this function. Now, is this good or bad? Well, the trick with this waveform is that I can design the waveform so that all these other peaks correspond to positions and velocities that are not physical or are not likely, at least. So for example, again with the close-up, if you can assume that it is not reasonable that your target is going faster than 800 meters per second, then this is perfect for you. Because with this waveform, you still have the same volume, but you are pushing the volume in positions that you already know that are not possible. So in this case, you are really gaining a lot. Let's see, waveform 8. So in this case, we still have a train of cardinal sign, but with a different period. And you see, we did push the ambiguities away in the Doppler dimension, but we are accepting more ambiguity in the distance dimension. You don't see it here because they're very close to one another for some reason. So the last waveform is, maybe this will be surprising for you. Looks good. Looks good. This is noise. I am just sending noise here. Of course, The trick is that this is the signal that I am transmitting. The trick is that when I do matched filtering, I have to use the same waveform, and so I have to remember which noise I did transmit. But in this case, you get a very nice result. And indeed, there are radar systems based on noise, and those are called noise radars. So basically, they do transmit noise to avoid ambiguities. And so this is it. I would say it's with very high probability on Thursday you will meet again Professor Monti, who will give an exercise session, I think about using GIS system, but I am not sure yet, so this is not 100% confirmed. We will meet next Monday, and next Monday we will start to talk about radar imaging. So next Monday is about generating images. I would strongly recommend to study this code and use next Monday for any question you have about this, because the next homework will be something similar. Okay.
I don't want to do it. Is this future?